Okay guys, bear with me. It's my first time multi-streaming to Twitch and YouTube, so I just gotta make sure it's all working. Let's have a look. Okay, it seems to be live on Twitch. Seems to be live on YouTube. Well, that was actually pretty easy. I should probably post this somewhere. Okay, how do I get the link for my own stream? I guess I can just link my Twitch. Okay. I just want to make sure the chat's working. Can I send a message to myself? Hello? Fantastic, it doesn't work. Okay, I'm gonna have to read the chat separately. That's okay, I guess. Hello, Ben. How you doing? Okay. Hang on, I'm just gonna organize this before I get started. I apologize if you're watching this later, and it's just me organizing things in the beginning. I expected multi-chat to work, but it did not. Shame. Oh, no, it's working now. Is it just really slow? But it's not on the screen. Oh, it is on the screen. Fantastic. Okay, cool. So I can see your chat down there, Ben. That's good. And I can't see my chat from Twitch, but maybe that's because it's me. I don't know. Cool. All right, I'm going to get into it in a second. First, I'm going to give a little overview of the code base, because if you have been following my streams, we did about 10 streams of working in C, and now I've moved over to Odin, and I'm using libraries. So I was in C, I was using no standard library, no vendor libraries, just all my own code, and it was fun. But then I thought about all the stuff that I need to do later in this project, because it is going to be a game, is way harder than building a standard library. And as much as I like that, it's just very time consuming. So I decided, you know what, screw it. We're going to use Odin, we're going to use libraries, we're going to use OpenGL, because I have the most experience with that. I did try Vulkan for a while again, and it's pretty cool, but it's got a lot of code to write, and I didn't quite get it. So I'm just going to stick with good old OpenGL, GLFW, and Odin. So we've got a lot of utility now. So I'll just walk through this code base a little bit. I'll just launch the. It's not really a game yet, but it's just a window. And if I move the cursor, you can see there's numbers in the little terminal down there are changing. That's because I'm rotating the camera. If I move my keys, you can see I'm moving on the X and the Z axis. If I press up and down, I'm moving up and down on the Y axis. That's pretty much it. I did have something in here before, a little field of dots or something that I could check everything was working. So it's all working fine. What we're going to do today is we're going to make marching cubes, hopefully, the whole thing. So what is marching cubes? Well, actually, I can just get a picture, because we have the internet. If we go to Google Images and we look at marching cubes, well, let's have a look here. All right, something like this Okay. Actually, I'm going to open this. Can I open image in new tab? Yeah, there we go. Right, it's a little bit blurry, but if you think of the terrain in a game like that dwarf game where you kill bugs and you mine stuff, Deep Rock Galactic, so it's used for that kind of terrain. I don't know if they use marching cubes specifically, but it looks like it. So it's a way of turning a voxel world or a scalar field, which is a fancy way of saying it, into terrain, or doesn't have to be terrain. It's also used for medical imaging and stuff like that. I'm going to be using it for terrain. And what does that mean? That means we've got to, well, we've got to compute a lot of stuff, so that's what we're going to do on the compute shader. I totally lost my train of thought there. Ben is asking, is there a reason I'm using OpenGL instead of Raylib? It's because I know for a fact in this game I want to do a lot of custom rendering work, and I don't want to have to go through Raylib to do the custom rendering. I'd rather just do it myself. If I was making something a little bit more standard, I guess you could say, then I would use Raylib because it's really easy to get started. It's got a lot of features and it's really nice. But for something really custom, which I know I'm going to want to do multi-threading, I'm going to want to implement you know, the compute shader, which means I need to set up fences and semaphores and things like that. I'd rather not be using a library on top of the graphics API for that. Cool. So that's what we're going to do today. And how does it work? Well, I've got this beautiful image here. So if you think of a voxel world, you might think of something like Minecraft, right? So what you can imagine is, rather than this cube being a Minecraft block, you can instead imagine that a Minecraft block is formed around this dot here. So like this, and then this dot has a value. In a normal voxel game, it might have a number of values that tell the terrain generator, hey, this this dot, that's not really in the middle, is it? That looks weird. Anyway, that this voxel is going to be this terrain type. If it's too high in the world, it's probably going to be air. If it's low down, it's probably going to be stone. And then if something spawns on it, it'll be rock or whatever. But the thing about marching cubes is what we're actually going to do is we're going to add a value to these voxels called density. And the way it works is we generate a mesh based on the density of 8 neighboring voxels. That's why I've got a cube here. It's actually about the neighboring voxels. So if you imagine, I'm going to have to look it up exactly, but let's just imagine this one is going to be a value of 1. And this one down here is also a value of 1. And then these are a value of 0 and 0, maybe these ones. We might get basically a, I don't think this is exactly correct, but you get a triangle basically in between the zeros and ones. Actually, I can actually do this, I think, if I just do this. There's 1, 1, 1, 0, 0, 0. So let's just say the value can be between 0 and 1, so it could be 0.5 or something. But we're just going to go for the extremes to demonstrate. So when we generate the mesh, we have to look at the edges, figure out how far along each edge we're going to generate the surface. So in this case, it's always going to be in the middle because we've got the extremes here. So 0 and 1. This one is going to have no edge. This one is going to have, no vertex rather. This one is going to have a vertex here. And then this one is going to have a vertex here, and then here, here, 0 and 1 here, 0 and 1 here, something like this. So we might get a shape, and then we have to construct the shape. I'm not exactly sure how it's going to look, but let's just say something like this triangle here and a triangle here. Triangle here. I don't know why there's a dot up there. That's weird. Did I move that by accident? Something like this. You might get something like this. I don't know if this is exactly correct, but you kind of get the idea. So we're generating the intersection of based on these values here. So that allows you to have those really cool looking smooth terrain, because you can imagine if this value was something like 0.5, then it would actually have less of a weight. So this would be further along here, or maybe the other way around, depends on which way you set it up. And then the you get sort of a slope instead of just a straight up and down. So I hope that makes sense. I apologize for the messy drawing there. And yeah, so for the code base, what we've got set up so far, we can load shaders, although we don't have any shaders to load. Actually, I think I have a simple vertex and fragment shader. They just take a position, projection, and view matrix, and then they just render them as a gray color. So that's very simple. That's what we're going to use to make sure our thing is working. But first, let's have a look at, actually I made a file for it called chunk. So this is what we're going to do. Generate scalar field on the CPU side. The scalar field is just the fancy name for the these voxels. So we're going to have to generate them, and they're going to be between the value of 0 and 1. And so usually you would use some kind of terrain generation. We're just going to use a random noise for this, just to get it working, and then add terrain generation later. And by terrain generation, I mean if you take random noise and you just generate that, it's probably not going to look anything like terrain. So you've got to actually add some constraints. So the top, for example, you want the top to be sort of a mountain or a flat plains or something. You don't want it to just be random bits of stuff floating in the air everywhere. So yeah, we'll do that later. For now, let's have a look at this. So let's say we're going to have a chunk type. Okay, and then on the chunk, we're going to have to store voxels. So we're going to have a storage buffer where we can store voxels, which we're going to pass to the GPU. Or rather, we're going to store the density values of the voxels. And then we're going to also need to somewhere to store the mesh. So that's going to be another buffer. And by buffer, I'm talking about buffer on the GPU. So in OpenGL, you can make a storage buffer, which just takes arbitrary values, and you can make a vertex buffer, which is for drawing actual 3D shapes. Cool. So let's have a look. We're going to make a scalar field. So let's just say when we initialize a chunk, we don't need to store the values anywhere, so we're just going to have a buffer. Scalar field buffer is going to be an unsigned 32-bit integer, and this is just an ID for an OpenGL buffer. When you create one of these, you just get an ID back, and then you've got to use the ID with OpenGL. And we're going to have a vertex buffer. Okay. And do we need anything else? We probably need a position, which is going to be vec3, maybe vec3i. Yeah, no, I'll just make it a vec3. That's fine. Okay, so let's just make an initialize procedure here. Chunk init. It's going to pass in a chunk. Actually, we don't even need to do that. We can just pass in a position and return a chunk. So maybe we should call this create. That seems fine. Okay, so let's actually break this down. Generate scalar field. Okay, well, why don't we just do that first? So we need to generate a scalar field, which means we need to use the noise library. Noise. Luckily, Odin has a lot of really cool built-in stuff. So we can just say noise, noise 3D, improve XY is the one I'm probably going to use, I think. Recommended for 3D terrain and time-varied animations. The Z coordinate should always be the different coordinate in whatever your use case is. If Y is vertical, okay, we want to use the other one. Improve XZ. So Y is up and down, so we want to use this one. Cool. So this is open simplex noise. That's going to give us a random value. I think it's between -1 and 1, so we're going to have to normalize that to 0 and 1. Well, we don't have to actually, we can just leave it. Oh, we need a seed. Okay, yeah. So we're going to pass in a seed here. So this would be a world generation seed. Like if you make a new world in Minecraft, you get that really long number. That's what this is. We're just going to set it to, I guess we'll just set it to to 0. I'll do that in a second. And we will, we're going to have to convert this because I believe their coordinate is actually, their vec3 is a 64-bit, yeah. So we actually don't want to use 64-bit. Because we don't need that level of, we just don't need that much, what do you call it, precision. We're going to actually say cast this to our kind of vec3, oh no, their kind of vec3, noise.vec3, and pos.x, pos.y, pos.z. Is there a problem? Yes, we have to get the results. So the value for this particular position is going to be just density, I guess. Okay, there's a problem. Oh, yeah, I need to convert these. Okay, convert these by adding F3064. Okay, there we go. Now, we're not just making one node in our chunk, or one voxel. We need to actually generate a bunch of them. So let's have a look here. So we need at least 8, right? So 2 by 2. But I'm thinking we'll make a chunk that is going to be 8 by 8. I should exit Steam. Get out of here. Why is it taking so long to close? What the hell? Alright. Junkai again. Hello again. I just emailed you, by the way. How you doing? Okay, so we want at least 8 voxels, but ideally we want a little bit of a larger size. So I'm going to say our chunks are going to be, let's just start with an 8 by 8 by 8. So we'll do X, Y, Z, just in case we want to change the size later. Make these 8 by 8 by 8. Oh nice, you're learning Odin as well? It's nice. I really like it. There's not really many surprises, which is good. So, got a chunk size, so basically we want to iterate over these. So from past experience, I usually iterate backwards, Z, Y, X. Don't know if that's going to be the better way to do it for marching cubes, but we'll see. Okay, we'll just do this a couple times. Oh no, it's the worst. There we go. Now, what are you working on in Odin? Great. So, iterating over the chunks, we generate the density for that particular voxel, and then we want to actually add pos is pos plus, and now we have to do this. Yeah. Okay, great. Actually, we could probably do it the other way around, right? So we cast these to F64. Oops. No, whatever, that's fine. I'm not going to worry about the minutia right now. You're writing a GUI app from scratch, huh? That's cool. Using Raylib. Nice. What kind of GUI app is it? UI library or something that is just I mean, a GUI app of some kind. Noise 3D improve. Yeah. Okay. Come on, brain. You can work. Okay. Generate scalar field. I just generated it in this variable and didn't store it anywhere. Yeah, so we need to store these somewhere. Density values, I guess. We can just make a temporary array here of float 32, or are they 64? I'm gonna make them float 32. And then we're gonna say the maximum size is gonna be chunk size X. Actually, you know what? Chunk count. Gonna be chunk size X. Maybe not count. Chunk voxel count or something. Hey Daniel, why am I looping through Z, Y, X? I don't know. I have it's like a memory from a long time ago that I should do it backwards. I don't know why exactly yet. I'm gonna confirm that later. Chunk size, yeah, so that should be fine. You know, sometimes you just do things and then you just do it that way in the future, but you can't remember why you do it that way. Or maybe that's just me, I don't know. Chunk voxel count, please, give me that, thank you. And we're gonna put that in the temporary allocator because we're gonna throw it away at the end. Don't care about that. But here we're gonna say, I'll just make this really easy and put a, not int, an index value here and just increment the index instead of doing the calculation down here. Density values index equals F32 density. There we go. So that should give us a slice of values between -1 and 1. That's what we want. Then, can you guys read the text okay? Is it big enough? Okay. What's next? Generate the scalar field. Okay, we've done that. Store in the storage buffer. Okay, well, why don't we verify that we've done this? So put a debug break here, and I'll import runtime, and we'll compile, and we can't because that's not the right name. It's called trap. And we can't because we didn't return anything. So we're going to return an empty chunk. Okay, we compiled successfully, and then, oh, we don't call this procedure, so we need to call it main. I'm just going to call it here. Actually, I'm going to call it down here because I know I'll run into a bug if I do it up there. Chunk underscore create. There we go. We'll just set the seed to 420, 69. Nice. And position, we'll just use the 0 position. Okay, good. Now let's have a look. All right. So what I want to look at here is, I'll make this a bit bigger. Density values. There they are. Dot data. Then this is an array of, what's the size? 8 times 8 times 8. Is it going to do that? Yeah, 512. Okay. Easy. All right, look. That's what we wanted. We've got values between 0 and, between -1 and 1, which is what we wanted. Well, I said 0 and 1, but we can work with -1 and 1. That's fine. Cool. Okay, so we can mark this one as done. Actually, maybe I should make them into little Little check boxes. Nice. That one's done. Now we need to store it in a storage buffer to access on the GPU. So that's what this SF buffer is going to be. Maybe let's call it storage buffer. Although that's a very undescript name, but that's fine. Okay, now to store it in a storage buffer, we need to make one. So we need to import OpenGL here. Not core. It's not core. Not gl.runtime. gl.create buffers. Okay, we're going to create a single buffer, and it's going to be stored in the chunk.storage buffer. We haven't got a chunk yet. We're going to make it up here. Okay, we're going to return it down here. There we go. So we've created a buffer, and then we're going to say bind buffer. Okay, target is going to be, I think, I gotta look it up. Let's see, docs.gl. It's been a while since I used OpenGL because I've been using Raylib so much. Okay, so we want bind buffer. I think we want this. Yeah, where is it? Yeah, shader storage buffer. Okay, cool. Okay, and the buffer is going to be this thing that we just made. And then what? Buffer data, and we make the target. I think the target is going to be what we just put here, right? And then the size in bytes, I guess. So it's going to be size of float32 times chunk voxel count. Yeah, yep. And the data is going to be chunk dot. No, it's going to be density values. Get a raw pointer to that. And then, no, it's not called raw pointer, it's called raw data. Usage is going to be, I don't know, let's have a look. Buffer data. Buffer data. Usage. Stream, we don't want to stream it. Static draw, we're not drawing it. Dynamic draw, dynamic read. Static read. I think static read would work. So the data will be modified once and used many times. Yep, and then read. Data are modified by reading data from the GL and used to return the data when queried by the application. I don't know what that means. Yeah, we're going to go with that one. What was it? Static read. I think that should be fine. Okay, because all we're doing in the compute shader is reading it, right? So now we've made a buffer. We've probably put data in there. I'm going to get rid of that trap. We return the chunk. Now we need to check it here. So I'm going to put what is the function called? Actually, we need to create a compute shader first. Vertex shader, compute shader, there we go. So we need a couple of things. What are they? Give me a second, I'm going to look up some stuff. Let me just look at the compute shader stuff here. Oh, cool. I didn't know Learn OpenGL had a section on compute shaders. That's kind of cool. Do they have... Yeah. Okay. No, actually, I need to learn about this. It's very confusing. The work groups. Because we're going to have to use this. Okay. I just want to see what a compute shader looks like. So, local size. Local size is 1 in every dimension, 1 pixel per work group. We'll alter this value later. Right. So he's using a compute shader to generate pixels, I guess. It's fine. Okay. Okay, let's have a look. So, what was it? Layout, local size, XYZ in. Okay. Layout, local size, X equals, I guess we'll just go with 8. That's what we're passing in, right? Chunks are 8 by 8 by 8. Size underscore Z equals 8 in. Okay. Right, yeah, we need a binding of some kind. So, STD, what's the difference between these again? 430 and 140. Second, STD 430. Okay, here we go. Where was it? There are 4 memory layout quantifiers shared packed STD 140, STD 430. Defaults can be set to the same. Packed sets all shader storage buffers to use packed. The default is shared. Okay. Packed means the implementation. Well, what just happened? Okay. I thought when you zoomed that it would keep your position on the page, but I guess not. Arrays of types are not necessarily tightly packed. An array of floats in such a block will not be the equivalent to an array of floats in C or C++. The array stride, the bytes between array elements, is always rounded up to the size of a vec4. So arrays will only match their definitions if a type is a multiple of 16. Okay, I don't think we need to care about this right now because we're just passing in floats. They're no longer rounded up to multiples of 6, so an array of floats will match. I guess we want to use this one, which is what I just typed in. So that's good. Layout equals this, and I think the next thing we need is a binding. Is it binding equals 0, or is it? Where is it? What the? This is not what I was looking at. Binding equals 0, okay. And then uniform, I don't think that's correct. Okay, I need to read about bindings, obviously. No, I don't want Leo AI. Please go away. Where's the button? There we go. Texture binding, layout binding, there we go. Okay. Buffer backed interface blocks and all opaque types have a setting which represents an index in the GL context where a buffer or texture is bound so it can be accessed, blah, 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 blah. Okay. So, okay, binding equals 1, STD 140. Oh, so you can do that in any order? That's a bit weird. Uniform, main block, and then a type. So what if I just say uniform? That's got a uniform and then a type and then a name. This has got a uniform, then a name. Oh no, that's a type. And the name, I guess, is data. Okay, got it. Okay, so we're going to say uniform. I guess I'll call it scalar field, and it's F32 array. Wait, is it the right place to put? I don't know. I think so. I think it's C-like. So that will give us access to the data, hopefully. All right. Okay, and then, oops. So we make our chunk. Okay, we need to access the compute shader. So how do we do that? Compute something. Dispatch compute. Well, that's nice. Number of groups, X, Y, and Z. So we set that to 8, didn't we? But we haven't use program. I guess we have to make a compute program. You dispatch the compute, and then is there a wait? I think there is a wait of some kind. Okay, so first we'll make the program. So we'll use shader, load, and compile. We'll pass in this shaders, matching cubes, comp GLSL cubes. Okay, and then the shader type is compute shader, and this returns the ID compute. Actually, does this handle program creation? I think it does. Link program, get program. Yeah. So returns the program. Okay. So this doesn't even give us access to the compute shader, just the program itself. Okay, that's fine. And then compute program, okay. Just going to assert it here. And, well, what happens if we run this? Probably something's going to break, right? Yes. Compute program, not okay. Okay, actually I have debug on. Did it tell me anything? No? Oh, that sucks. What if I run it in here? Wait, why did I do that? No difference. Okay, that's okay. That's weird. I would have expected to see something because we're logging to the debug here. Let's just see. I'm going to import format. Maybe there's something wrong with the buffer that we're logging to. I'll just print to standard out instead. And maybe here as well. FCM does not exist. Yep, that's right. This is not a cryptocurrency. Very good. Okay, we got an error. That's what we expected, but did we get a message? Unexpected word layout at token layout. Well, that's good. We know the problem is a syntax error. What just happened? Right. I guess something is wrong here. local size, local size, local size. In, and then layout. Is that wrong? Do I have to put, do I have to use core? I don't think so. Maybe. No. Unexpected reserve word layout at token layout. 0.5. So it's got to be this one, right? Oh, yeah. I think it's this. Okay, we got another error. Is it different? Yes. Good. Okay. Uniform buffer, STD430 layout, enable before use. Incompatible with uniform blocks. Okay. Okay, I need to obviously learn more about that. What happens if I remove this keyword? Does it just break? Expecting reserved word in or out? Oh, this is in. Does that work? I don't think so. Okay, I need to look up something really quick here. I did find a compute shader marching cubes example on GitHub. But I don't remember where it was now. Compute shader, was it OpenGL maybe? Okay, so there is an example here. I'm gonna not just copy the code because I don't understand it. I don't really want to do that. But basically, I'll just show you the code here. Blah blah. Oh, that's really big now. Yeah, so we need read only and buffer. So I need to figure out what these are. It's not even mentioned here. So here it says out. Oh yeah, that's for a fragment shader. Okay. I don't know, man. Is this wiki any good? You'd think it would have this somewhere. Apparently this doesn't exist. So there's nowhere where this keyword shows up in their own wiki. That's interesting. Okay. Read only buffer. Input field. Yeah, okay. I'm just going to close that. I'll leave it on this side. Okay. So I want to learn about this. If anyone can point me to any documentation that speaks about this, that would be great, because the wiki doesn't seem to have anything about it. Okay, we've got another bug. What's the bug this time? Unexpected token. Expecting double colon. Okay, interesting. I guess that's this. That seems a bit weird. I just closed the other one, didn't I? Oh, yeah. I'm using F32. That doesn't exist in shaders. We need to use float. Okay, it's C-like, it's not Odin-like. Okay, that should hopefully work now. Okay, cool. Our shader is compiled. It's running. Don't know if it's doing anything. So I'm gonna put it in here in the render loop, which means we're gonna compute on every single frame, but that doesn't matter because we're not doing anything with the compute shader. And then we can open it in render doc. I think it's the same last settings. Yep. Okay, good. Capture the frame, press escape. Now we should be able to see in here, hopefully, some data. Program 48. Shader for, no, I don't see anything here. That's not good. Shader 47. I'm not seeing a buffer. Maybe because we didn't access it, it got compiled out. So I guess I got to do something with it. SF data. There's a bunch of things like local GL, local something something that you can. Okay, this search sucks apparently. Local invocation ID. I think it's called. Okay, cool. This is a great wiki. I'm very glad they have this. So you have to search Google to search their wiki, I guess. Oh no, this is not their wiki. This is the registration. Local invocation ID. Oh, it probably says it on this page, you know. Here it is. So, index of the current work item in the work group. Oh, by the way, just a little random tangent here, but if you were watching the streams before and I said I was going to program an entire game from scratch on stream, I can't do it. And I'll tell you the reason. Because when I put that constraint on myself, I stopped working on it completely for a few weeks. Because the thought of having to do stream is adding extra friction, and then that just made me do other things. You know how it is, you got to make it easy for yourself to do things that you want to do, and that was making it harder for myself. So yeah, there is going to be offline programming, but I'll try to share as much as I can. Okay, so if I don't understand what the work groups are, then I don't really understand what this is exactly, but I know that it's going to be different. So I can just use this to index this array or something. Right, GL local invocation ID. So UVec3. I don't need to, what am I doing? Maybe index equals .x times local size x. How would we do it? Plus .y times local size y plus z or something? Plus, yeah, the same thing again. .y times local size y plus local, not local size, but .z. I think that'll work, but then I don't know what to do with this. Let's just say can't use F32. Can't use that. Yeah. Okay, we got a failed compilation because why I clicked the wrong thing. Narrowing of type vec3 to float. Okay, undefined variable local size x and y. Okay, good to know. So apparently these are not actually variables. So I'm just going to put 8 here for now. 8, and then what was it saying? We narrowed something. So this is, oops, implicit narrowing of type from vec3 to float on line 13. I'm guessing that's this line. How is this a vec3 if we index into an array of floats? Does that make sense? That doesn't make sense to me. Oh, because I'm indexing it. Yeah, I'm stupid. This should be uint or something. There we go. Okay, are we computing anything? No, let's open it in RenderDoc. We'll just run it again. Save the capture. No. Capture the frame. Okay, we dispatched compute. Okay, I'm not seeing anything in here. Pipeline state, shader 47. No. Doesn't look like it. Okay, what else can we do in here? I can't say for sure that this is getting compiled out, but I think it probably is because we're not doing anything with any of this stuff. Maybe we make an out buffer. I guess we need to do that anyway. So write only, is that a thing? Apparently. And this will be our vertex buffer, which is where we're going to store our vertices eventually. But for now, I'm just going to put in a bunch of floats. So it doesn't have a size. If there's no size, what does that mean? I don't know. So I'm going to have a look. Vertex buffer index equals SF data index. Okay. So basically we're just transferring from one to another. Maybe we should multiply it by 2 or something. Okay, that means we're doing some work here. We're definitely doing some work. Okay, so we've got to make a new buffer for it. Where did we do that? I made it in the chunk, didn't I? But in this case, hang on a second. We didn't bind the buffer. I think we need to use this one. Why do I think that? Bind buffer base. I think that's the one we need to use. Well, that's probably why we couldn't see the buffer. We didn't bind it. It's weird that that's not an error when we're apparently using it, but it's not bound. I guess that's why people hate OpenGL. Even with debug on, wait, bind buffer base, here we go. Bind a buffer object to an index buffer target. Okay, so we're binding a shader storage buffer, that's right. The index is the index of the binding point within the array specified by target. What the hell does that mean? The name of the buffer, okay. What is the index? It's equivalent to calling this with offset 0 and size equal to the size of the buffer. Okay, great. Invalid value is generated if index is greater than or equal to the number of target-specific indexed binding points. I'm guessing it's this, right? This is binding 0, so we'd bind to index 0. The target is going to be compute, no, what is it? It's here, shader storage buffer. Right, here we go. Shader storage buffer. Is that it? Yeah, I think so. Index is going to be 0. Yeah. So fantastic. So we're binding the buffer now. But I did some other stuff in this compute shader. I don't even know if it's going to compile anymore. Okay, it is compiling. That's nice. Let's see if we can get the values. In RenderDoc. Oh, buffer 46. That looks like we got something. It's our GL static read buffer. Oh. I realize this is probably really tiny for you guys, but let's see. Buffer 46. Where's the data? Initial contents. I can see it in... Where can I see it? Click this. View contents. There we go. Okay, now we're going to make a struct for it. So I think we can say struct... no, I don't think we need to make a struct. I think we need to say float data and then apply. Hey, look at that. We've got our values on the GPU. So these are our values between -1 and 1. That's exactly what we needed. Fantastic. Okay. So that's confirmed. Now, we still need to actually make that the buffer. So we'll do that here. Create buffers. So we'll make 1. And we'll make it in the vertex buffer. So basically just... I think we want to set the size, right? So how do we do that? Find buffer. Vertex buffer. No? Is it an array buffer? I think it's an array buffer. Whoops. And then buffer data. Buffer, what was that? Buffer data size? Did I see that? No. Target is going to be chunk. No, that's not the target. Target is this. So I think we can reserve memory in the buffer by specifying a size here and then sending a null pointer to the data. So if we say the size is going to be, so this is kind of the annoying thing about arching cubes. We don't know what the size is going to be because we don't know what the generation is going to return, like how many triangles are going to be in this, which means we've got to generate basically the maximum amount. So I'm actually just going to use this size now. And then I'm going to set nil, and we're just going to return a bunch of floats that are doubled, which is what we planned. So I think here if we do bind buffer base gl dot, can I use it as a storage buffer? No, I probably need to copy it, don't I? Yeah. Whoops, excuse me. Okay, here's what we're going to do. I'm going to make a storage buffer 2 because we're going to delete it later, but I just want to make sure we can swap between them. I mean, I want to make sure we can operate on things properly. So storage buffer 2 is going to be our temporary buffer that is going to be not static read. What were the options again? Wait, was this the wrong buffer data, right? Yeah, buffer data, not bind buffer. We want dynamic copy. Yeah. Okay, this is going to be storage buffer 2. Oh god. I should have just done this. Fantastic. Okay, don't worry about the vertex buffer right now. Go into the shader. This is going to be binding 1, write only, buffer, vertex buffer, float, vertex buffer. That's fine. And in main, we want to bind shader. We'll just do the same thing again. This is going to be binding 1. And there, and then we want to use this program. Actually, I want to test it first. Okay, good. Nope. Capture and exit. Okay, dispatch compute, buffer 47, contents, and I gotta view it as floats. Apply. So let's have a look. 0.8 is that. Yeah, okay, that worked. So we doubled the values and we sent it back to the, well, we doubled the values. Hello, I don't know how to say your name. Sans el Loquendro? Loquendero? We are making marching cubes on the compute shader. So basically we can get terrain that looks kind of like this. So right now we've got a buffer set up on the GPU side, and we just sent some data to it, and then we doubled it to make sure our compute shader is working. And it is. However, we don't want to do that. What we actually want to do is generate triangles. So I guess now comes the hard part. Stream dropped out for a second there. Hopefully it's still recording and everything. Okay. So we verified that we can make the compute shader do things. That's great. However, this is not really what we wanted to do. So we've got to look at the implementation for marching cubes, which is going to be old classic Paul. Actually, you know what? I'm going to look at the one that someone else wrote. But I'll link you to the one. Actually, I'll show you the one I was going to use. So this is the one that I've used before. Paul Burke, marching cubes, polygonizing a scalar field. Okay, this guy's website, you can tell he's serious because the website layout is like this. This is really good resource. I've used this to do it previously on the CPU. I've never done it on the GPU though, and these tables are going to be useful for us. But you can see the whole algorithm is here. There's no SIMD, no threading or anything, so you can optimize it at your leisure, I suppose. But I think what I'm going to do is actually, you know what? We will use this. I'll use this and I'll try to figure it out from here. So basically, there's a few steps. The first step is we need to make a cube out of the voxels. So let's say this is voxel 0, 0, 0 down here in the corner there, as in 0 on the x-axis and the y-axis and the z. And then let's say that this is the, let's say that's the x-axis and that's the z-axis. Okay, so then this would be 1, 0, 0, and then here would be 1, 0, 1. So basically we've got to take a voxel, which would be this one, and we've got to grab all of these here, which you can already see is highlighted in orange, and then we've got to run it through a function that's going to calculate the distance between the points where the vertex for the mesh is going to be generated. And to do that, there's this crazy table with all this, all these values in it, which I'll show you in a second. Actually, do I have it in the code base? I might have it in here. No, I don't. I thought I had it. It's fine. We can copy it from this website. Okay, and the way that we figure all that stuff out is we make something called a cube index to figure out what kind of cube it is. Actually, I'll show you this. So you can see, where's the cube index stuff? Is it up here? Doesn't actually have it here. But basically there's a set number of cubes. So if we go to marching cubes on Google, go to images, look at this. You can see there's a set number of configurations. And I think it's 16. And then there's actually 256, but it's just rotated versions of those. So we need to figure out which one we have and then generate it. And yeah, so you can see you can make pretty cool kind of stuff with it. I've never seen this website before. What is this? app.cpp, isosurface.cpp. So probably this one. Oh no. Oh no, I can't read C++. Okay, never mind. We'll just use this one. So we need to generate the cube index, which is the kind of cube that we have. And the way that we do that is we go through the 8 edges, but first we need to, oh not edges, but vertices, voxels. First we need to figure out how to get the 8 of them, right? So we'd have, the first one would obviously be 0, 0, 0, but that would be, I guess, this index here. So SF data index. Now that would be the bottom left corner, let's say. But then, yeah, then we've got to figure out, so we've got to do this in a loop basically. Okay, I think this is going to be fine. This shouldn't be very hard, but brain is not working too well. You know what, I'm going to look at a reference. I'll put it on the screen so you can see what I'm cheating from. Okay, it's this guy's, his name is German Uncle. That's kind of funny. He's got a compute shader here. Let's just have a look. So the thing I was talking about was when you create the, where is it? Cube index, it's got to be here somewhere. Oh no, it's going to work differently, isn't it? Okay, what is this? Make sure this is not a border cell, otherwise neighbor lookup in the next step would fail. That's a good point. We should do that. So that's because if you can imagine you've got a larger set of these, so you need to make an 8 by 8 by 8. And if we do something like this, you can imagine we're going over this big field, and then you get to the end, and then you're like, okay, this one, make your box, and it tries to grab something here, but there's nothing there, so it's going to fail. So we need to make sure we don't iterate off the edge there, which is quite good. Okay, that's good. And then the index. What? Oh, that's simple. Local invocation ID is the index, apparently. What I did was strange. He's got a size of 9. Interesting. So voxel data. Oh, that makes sense actually. I think. Because you always need one off the edge to calculate, like I was just saying. But anyway, what is this? Oh, this is generating the cube that I was just talking about. So the 8 values. Oh yeah, it's really easy actually. Just get the index, add 1 on each axis. Okay, and then turn the information into a triangle list index. So the triangle list is that table I was talking about. It looks pretty gnarly. It looks like this. And I'm pretty sure everyone just copies it around I did actually do the 2D version manually once. I think it was last year, where I worked the whole thing out in 2D from scratch without using anything, and then made the table myself. That was pretty fun. Kind of time consuming though. A triangle type index. Right, yep. Okay, yeah. So basically, the way this works is we iterate through each of the 8 points, and if the value is above the threshold, which is called the ISO surface usually, then we OR this number using a bitwise OR with 1 shifted to the left for which bit it is, and then we can use that into the table that we just saw as an index. So that gives us 256 potential values. Okay. Set up all neighboring vertices. Okay. Neighboring vertices. Right. Well, let's get the first part done first, which is basically this. This I usually copy the original and call it a grid. So we'll do that. That's the wrong thing. I need to look at this. Data cont index. Okay, what is that? I should probably look up what that is. Cont index. Cont index. Oh. Okay, so it's what I did basically. Chunk size times z plus chunk size times y plus x. Didn't I do that? No, I did it the wrong way. See, I knew I got something wrong. Z times x. Yeah, there we go. And I guess we should pass in the chunk size. Actually, we're just going to hard code it for now. That's okay. Right. So what we can say is basically this. I'm going to call it, it's going to be 8 floats, and I'll call it grid. Grid 0 is going to be, I'm just going to copy it actually. Okay, there we go. Okay. Do you guys do that thing where you copy someone's code and then you just change the style to slightly fit yours because you don't like how they've done things just a little bit different? I don't know, maybe that's, I think that's pretty normal actually. Okay, that's fine. Why do these have no space in between the plus signs? See what I mean? There we go. Okay, we know what that's doing. We don't have to worry about copying that, right? Scalar field data. Okay, we've made our 8 points. That's good. And then I gotta stop going to this. I'm gonna close it. Good. No, that's the wrong one as well. I'm gonna close this one too. There we go. Okay, good. Turn this information into a triangle list index. Yeah, right. We went over that. Usually called cube index. Started at 0 and then 4. Wait, is it doing it a different way? No, same way. I is less than 8, I plus equals 1, and then we want to say for each one, if SF data I is greater than the threshold, which in our case is 0, because we're using values from -1 to 1, so I'm setting the threshold to 0 for now. Actually, I'm going to set this as a variable up here so I don't forget about it. Okay, it's greater than ISO surface, then we want to do cube index or equals I shifted to No, 1 shifted to I. And I'll just put parentheses around this because I never know. I think that would have been fine, but anyway, that's fine. So now we've got our cube index. Now we can look it up in the triangle list, which I don't have, but I'm just going to copy this one. Give me that triangle list. So I'm going to put that at the bottom. Hopefully I don't know if the order matters in shaders. Okay, triangle list. It's here. Very good. Hey, that's interesting. I just realized something. It doesn't have the other list. Huh. Okay. That's fine. Okay, I want to stop drinking that. Okay, so hopefully by now, but we can't tell anything because we can't debug anything, we've got a cube index. Now I've got to set up the neighboring vertices. What is this again? Okay, I'm going to look it up. Paul Burke marching cubes. So I really don't like implementing things if I don't understand it. I think it's bad practice, at least somewhat. You can't understand everything all the time. Fill the vertices where the surface intersects the cube. Oh, that's right. That makes sense. So there's a maximum number of 12 vertices, I think. And they can make up to 5 triangles per marching cube iteration. So that's what this is about. Don't know why it's called neighboring vertices. I guess it makes sense. Let's not get hung up on the details. I just want to say thank you to my German uncle for providing this reference. He's a very cool guy. And then we just iterate over 12 times and he sets them to 0. Why does he do that? Are they not initialized to 0 in this language? Well, I'm not going to take the risk since... Actually, I'm going to look it up. OpenGL initialized to 0. Are arrays initialized to 0? No, I want OpenGL. Does Google just suck now? It's fine, I'll look it up later. I'll just do it. Okay. Yeah, we can't do that. It's to be like this. Fx3000. That's fine. All right. Create vertices. Okay, so this is where the magic happens. And it passes in the local invocation ID, which is the position, X, Y, and Z. And then the vertices, and then the vox data. But isn't the voxel data just a global? Oh no, he just made that. Vertices, voxel data. Okay, let's have a look. Right. All corner points at the current cube. Fine. C0, C1 to 8. These are the corners. Find the 12 edge vertices by interpolating. Right, so that's this. So it's equivalent to this vertex interp. If we look at this here, which is basically the same thing. Okay, I'm going to actually change how this works later, definitely. But for now, we'll just copy this implementation and see if we can get it working. So I don't know that I have anything to change here, so I might just copy it. And of course, change a little bit because it's not going to have the same names and stuff. You know what? I'll write it. It's fine. Writing is fun. Okay. Create vertices. So we're going to do this part. I don't actually think we need to put this in a function. We can just write this here. So let's see. X is going to be, I see. It's kind of annoying writing global invocation ID everywhere. Was it global? Or was it local? Local. Yeah. X times voxel size. What is voxel size? 1. Okay, well, I'm not going to change the voxel size to anything but 1, so I'm going to leave that. In fact, we don't need to do, I guess we could do that. Yeah, that's fine. Okay, now we're making the corners, very simple stuff. Corner 0. So this is the bottom left corner in our case, X, Y, Z. And this is going to be, okay, so we're going on the X-axis first, and then Z, no, and then Y. I think we should go Z instead. I don't know that it matters. You know what, I'm gonna copy the same, and we'll figure it out later. So that doesn't need to be, yeah, +1, and then Y, and then Z, yeah. I'll copy this. C0, C1, 7. Okay. So we're going to go with what he's got here. So now on the y-axis. Now on the z-axis. Now x and z. Now all of them. Are you kidding me? Thank you. And y and z, alright, great. Okay, so that'll give us our corners. Very well. Now, pos is where we're storing the vertices, so that's our vertices right here. So we can say vertices 0 is equal to, and this one we probably will make a function for create vertex c0, c1, sf data 0 and sf data 1. That is, I think, equivalent to this section here. It's interesting, there's if edge table, so he doesn't do that. Oops. He just always generates 12. Maybe it's faster, I don't know. Okay, yeah, C1, C2, C2, C3, C3, C0. Back to the beginning again. Okay, that makes sense. C0, C4. So this is going to be the vertical ones, right? 0 and 4, yeah. 1 and 5. 2 and 6. 3 and 7. So these are all the edges that we need to look at here. So we basically go around the bottom. Actually, is it the bottom? In this case, it's the front and then the back, I think. Yeah, the front, then the back, and then the other 4. I need to make sure we update all these. Five, 6, 7, 4. Yeah, right. 4, 5, 6, 7. Yeah, so really I think the order didn't matter and we could have done it in a different order, but that's okay. Now I'll make this function here, create vertex. So we're going to create a vertex between 2 positions, that's the 2 corners. And what's D0? What is that? D0 is... oh, the data, yeah. D0 and D1, right, okay. Very well. So we get the difference between them. That's cool. And then if the difference is greater than y 0.000001, why are we doing that? Alright, otherwise they're in the same spot and we should do halfway point. Is that right? Yeah, I think that's right. We don't have ISO level, so where is it? Didn't I make that? I thought I made that. Oh, I called it ISO surface. I meant ISO level, and I'm actually going to put it up here and make it a constant. ISO level minus D0 divided by... so this is just an interpolation function. We're going to change this later, so I'm just going to use his one. And this will just give us a midpoint, I believe. Okay, great. We've made our vertices now. That's good. Now we can probably... well, let's just finish it off. We've made our vertices, and then we want to make the triangles from the vertices, right? Yeah. So these vertices are just the 12 ones that may or may not exist on the cube itself. Triangle vertex indices. Yeah. Triangle type index. This is the cube index, right? What is triangle type index? Yeah, cube index. Okay. Vec3 current normal. Why is there a normal in here? Oh, he probably added normals to his buffer. Is that right? Yeah. So we're not going to add normals, which means, let me look at this. We're just going to do something like more like this. Maybe we'll add normals later. So I is going to equal 0, and then triangle table, no, triangle list, cube index I is not equal to 1, no, not equal to -1, because we're going to iterate through these, basically through these numbers until we hit a -1, and then we're going to stop. but it should be in groups of 3. So you can see there's 3, 3, so that's 1 triangle, that's 2 triangles, this one's 1 triangle, this one's 2 triangles. Does that make sense? This one's 3 triangles. I gotta stop saying, does that make sense? Alright, we're gonna go through here and we're gonna say vertex buffer. Oh yeah, triangle count. Triangle count equals 0. Triangle count. I just realized something. We can probably just use an I here, I think. Because we're going to iterate by 3s, and then we're going to say I plus... Yeah, we'll do this. I think this will work. Vertex list. What is vertex list? Oh, that's our vertices. Vertices. Triangle list. Cube index. I plus 0 again. Okay, I think that's going to give us our result. We don't... I mean, we could store the triangle count somewhere. Okay, and then we just get rid of that. And let's have a look. Okay, now I'm going to have to look at Python code now, which I don't really know very well. Actually, you know what? Let's just run this first. See if this even compiles. I have no idea. Of course it doesn't. Okay. Data is not a variable. Swizzle mask element not present in operand Y. Okay, let's have a look at these one by one. Okay, here we go. Alright, line 20. Data is not a variable. That's correct. It isn't. Right, what was this supposed to be? This is supposed to be grid. And this is supposed to be SF data. Good. So that should fix the stuff in line 20, hopefully. Although, actually, this is a... right. Yeah, that doesn't make sense. I don't need to compile it again. I don't know why I did that. But we've got another error here. Okay, what's the problem? Line 39. What's... Oh, yep, there's no I here. Very good. And line 40, undefined variable, that's fine. Create vertex. Apparently this doesn't exist because you do need to forward declare in this language. Okay. Which means triangle list is not going to exist. And you know what? I'm going to put this in another file. Marching cubes triangle list dot glsl. And then in here, I'm going to say import. I think it's import, or is it include? No, it's include triangle list marching cubes triangle list.glsl. I think that's correct. And let's have a look now. Okay, not quite there yet. OpenGL does not allow include directives, doesn't it? I thought it did. What? Didn't he use one, in fact? Look at this. This is in a different file. Oh, it's pragma include. Okay. Gotcha. Thank you. So that's a compiler command. Now what? Okay, let's have a look. Almost there. Well, almost ready to test anyway. Unexpected identifier expecting comma or semicolon at token vertices. Oh yes. You know, programming in Odin for so long, I just forget semicolons all the time. Whoops, what just happened? There we go. Undefined variable triangle list. Is it actually undefined? That's not good. We want that to be defined, please. Okay, cube indlux, and that's definitely incorrect. So many typos. I forgot to post in Discord that I was going live. I'm going to do that next time. Triangle list, cube, inidex. Did I just do that right now? Alright, but did we get... Yeah. Triangle list is still undefined somehow. Okay. Is that because it's constant? No. Triangle list. What's the problem here? What about this one? Triangle list, pragma include, very good, and then do I need to include pragma once? Maybe I do. I don't. Why would I need to do that? Well, obviously I wouldn't want it to exist multiple times, but that is not the problem. Okay, good to know. Narrowing of type vec3 to float on line 86, so we'll fix that one first. Let's have a look. So, oh yeah, that makes sense. Yeah, I can't, there's no LSP for this, but vertex buffer is floats, yeah, and then this needs to be I plus 0, yeah, and then this needs to be 0, 1, or maybe dot x. Wait, that doesn't make sense. Right. We're making a triangle, we're not making... Okay, I need to rethink this. So this is going to be dot x, y, z. That's probably an easy way to do this. But anyway. This is going to be 3, 4, 5. No. I don't want to do it this way. This is not good. I'll just make this a buffer of vec3s instead. How about that? Doesn't have a capital, does it? No. And then this would be different, right? No, that doesn't make sense. P, hang on. No, it is. It is just 3s. Okay, I think that's correct. Okay, we still have this problem with the triangle list being undefined. Okay, you know what? Marching cubes triangle list.glxl. Marching cubes triangle list.glxl, but maybe it's because it's in a different directory, perhaps. No, I'm just going to put it in the same file for now. This is bothering me. What? Okay. Can I define it up here? Probably not here. That's fine. I just have to go to the bottom every time. Okay, last errors are these. 343, narrowing of vec3 to float, which I think is where we're making our triangle. So this code is incorrect because this is a vec3. So this should be, I guess, plus 0, plus 1, plus 2. Triangle count is 1, but then that's gonna overlap, isn't it? Pretty sure this is wrong. Okay, well, something happened. Oh, it's doing the compute on every frame, which is laggy. Let's have a look. Okay, we'll just save that and have a look at the data. So looking at the compute shader again, look at the resources, buffer 46. Actually, we don't want to look at buffer 46. We already know that one works. Let's look at buffer 47 and look at it as vec3 array. Is that going to work? All right, cool. Well, I have no idea if these triangles are real triangles. We've got 127 of them. So I guess we should just try and draw them. What is this? 2 issues in the capture. What are the issues? Buffer object 19 is bound to storage buffer. Usage hinges static read. We'll use video memory. Yeah. Isn't that what I wanted? Okay. I don't really understand what this info is about, but thank you. Cool. All right, we got the data in there. I don't think that's correct, though. In fact, it's definitely not. Yeah, definitely not correct. That's not a triangle. You can't have a triangle with... actually, no, that could be a triangle. 0, 1, 2... Yeah, that could be a triangle. So... Is there a mesh viewer? Yeah, but it doesn't make sense because there's no vertex. Okay, I'll try. Not sure exactly how to do this, but we got this buffer back, so we're just going to compute it once. I'm going to do that here. So we know the compute is doing something, right? Because we're running it every frame. Now I've got this storage buffer 2. Oh yeah, that was the problem. Why we shouldn't be binding storage buffer 2. We should be binding the vertex buffer. And then this should be a array buffer, I guess. Oh no, this should be a storage buffer. You know what I want to know about these buffers is, can you define the type and use the buffer, like define a different type and use the same buffer? So for example, use a storage buffer in the compute shader, put vertices in there, and then use that same buffer in the vertex shader, or do I have to copy the data from one to another because they have different types of uses? So if I make this an array buffer, for example, or if I bind it as an array buffer, what's going to happen? Voxel count, size of 32. So what we're going to do is we're going to say size of 32 times voxel count. So if there's 5 per cube and there's 8 by 8 by 8. So we're going to say this is actually going to be 5 triangles. So times 3 times 5, that's going to be the size that we might get in there. And then what if I make this a array buffer? What's going to happen? I'll just get rid of storage buffer 2 for now, or forever. And I will put this back down in here so I can see it in render doc. Okay, oh, that was a lot of errors that I just saw. Let's run that again. Actually, before we run it again, let's look at the resource. Contents of buffer 47, there's nothing in there. Yeah, okay. What were those errors that we're getting? Probably we're using the wrong buffer type. Let's have a look. Yeah. Invalid enum. Yeah, okay. So we can't do that. Okay, that's fine, I guess. Yeah, it's triangle list. Okay, so we're going to bind vertex buffer is actually a write-only buffer for storage. Yeah, it's not really the vertex buffer then. But let's see how many triangles we get. We got 128 last time, right? Or 127. I think we're going to get more. Maybe. Launch F12. Come on, close. Thank you. I wasn't getting the input because it was too laggy. This NVIDIA thing is so annoying. Get out of my way. Okay. Buffer 47 has no contents now. That's weird. What? Huh? Yeah, the initial contents, yeah, but that's strange, because all we did was revert back to what we had, right? Shaders. Oh, I know what I did. I made it a vertex buffer here. No, I didn't. I bound an array buffer and I said, yeah, okay, that's totally wrong. Can't do that. Okay, so I think what I'm going to do, okay, I don't know how to, let's explain this. All right. Get out of here, masterful drudge. Don't want your kind. Okay, so what we're going to do now is, I think what I'm going to do is I'm going to have the compute buffer. Let's just draw a little buffer here. So we've got our compute buffer. This is where our scalar field values are, the 0, -1 to 1, whatever. And then that gets sent to the compute shader. Okay, compute shader, and then it writes into another buffer, which I'm going to call vertex buffer, which is going to be confusing in a second. So I'm going to call it vertex buffer 1. Okay, and then what we're going to do on the CPU is we're going to make vertex buffer 2. And we're also, on the compute shader, we're going to actually write a value which is the triangle count. How many triangles are there? Then we're going to make vertex buffer 2, and it's going to actually be only the size that will fit these triangles. We're going to copy the data from here to here, and then this is going to be what we render. And then maybe later, what we'll do is we will actually do all of this stuff and then add it to a big buffer and then draw it all at once, but we'll see. I don't know if that will be good or not. So I need to figure out how to get a little value back. I can probably just make a little binding, but that's, I mean, it seems inefficient, but we can do it right now. So if we go to the compute shader here and we just make another binding here, layout, that's fine. It'll be a vec4 binding 2, write only buffer. It's, I don't know, metadata. And this is just going to be an int, which is the triangle count. Maybe there could be some other metadata we want to send back, but actually we can't be that. It can't be that. We'll call it MD triangle count. Down here, MD triangle count equals triangle count. Okay. So now we should be able to get that data back out on the CPU side, I think. Don't know how to do that yet. But let's just say we can. It's getting close to 7 p.m., which is when I have to go. Okay, so we're dispatching our compute, and then we also want to bind buffer 2, which is going to be a storage buffer, and that's just going to be metadata buffer or something. I mean, this is really kind of crazy, but anyway, that's fine. Metadata buffer. Just make that a U32, and then we'll just do the same thing as this. Although actually, now that I think about it, we could just write it to the storage buffer since we're not using this anymore. But we'll do it this way. Metadata buffer, and it's a storage buffer, and it's just going to be size of 1 integer. It's going to have no data. Is that even? I don't even know. Dynamic copy. Cool. Okay, so we've got our metadata buffer that we're binding here. We're going to put the triangle count in there, and we'll see if we can see what that is. Is it going to work? Okay, that's good. We're loading. Okay, we're going to launch, capture a frame, and exit. I should just make it capture the first frame and exit straight away. There is an option for that. Dispatch, data resource monitor. Okay, so I've got this shader, no, buffer 48. Yeah. Buffer 48 has value 1. What? That doesn't seem right. I did have the triangle list here. I thought I had it. Oh, wait, never mind. That's the same file. That's what I'm looking for. Wait a second, what? This one, okay. MD triangle count. Well, that doesn't sound good, does it? It doesn't seem very good to me. It could be because of something to do with this GL local invocation ID. So you might want to run this shader, compute shader, for every grid cube, and then this might just be running the first grid cube, and then the first grid cube we only get one triangle back, which is entirely possible. Yeah, okay. I'm gonna have to probably do some learning about exactly how this stuff works, the local invocation ID, because I might not even be getting to the other grid cells, as in the other 8 voxels. So maybe, actually that makes sense. If I look at the call here, wasn't there a dispatch compute? So the number of groups is 8. Oh, I see. Okay, I think I understand what's happening. So this metadata buffer is going to be overwritten by each compute thread, and it's going to be 8 by 8 by 8 compute threads running, and they're just going to clobber this data here, which is not what we want. So I guess what we could do is we could make the metadata buffer fit the size of the voxel count times an int32, and then in the compute shader, when we set the MD triangle count, we actually use the index, which is, wait, it's not index, is it? It's, yeah. So we've got X, Y, and Z down here. We can use those ones. X, oh no, they're floats. X times 8 plus Y times 8 plus Z. Or is it Z times 8 plus Y times 8 plus X? Does that work? No, we got an error because, probably because we're using floats, right? Yeah. Okay, I thought so. We'll just say xi equals gl dot, no, gl local invocation id dot x. Okay, good. And I'll set this up to do Q frame 0, and we'll just capture 2 of them. And that's about it. Oh, hey bot, how you doing? All right, we captured the frames. We can just exit now. Okay, fine. Just woke up, huh? Nice. What time is it there? Okay, we've got buffer 48. Hopefully it's got data this time. Yes, it does, but it's all 1s and 0s, which is weird. 8:17. Nice. Got the whole day ahead of you. That's great. We've been implementing marching cubes Well, trying to anyway. On the compute shader. So there's something I'm missing here, which I think is going to be revealed if I look at this. Except that I don't really know Python, so this will be interesting. Create geometry node. Don't know what that means. Create a dummy vertex data object. Okay. Okay. Put our node in the scene graph and apply. Okay, that's not what I want. Add a compute node to. What does that mean? I have no idea what any of this stuff means. It's got a scene graph and then you add compute nodes to it. But where do you actually call the shader? Like this says. Okay, here's our shader. Geometry dot. So that's the drawing shader. So here's the compute shader. We're loading that. Yeah, we're setting it. Setting the inputs. That's cool. But then it doesn't. Oh yeah, we need to do something after this. So we create the compute node. Okay, and then what? Cool, we've created it, but when do we run it? Apparently not in this file. Okay, that's fine. Maybe in main. Okay, so it's created here, and then reparent, and then chunk. What? Yeah, I don't know, man. Python is weird. We learned it at university, and it was pretty different to other languages. Yeah, I think people just write it differently too. So there should be an update function. Okay, so set the input to threshold. Great. That's fine. And then task continue. What is a task? There's no types, so it's kind of annoying. So task is update? No, task is, yeah, base dot task. What is base? Show base. Okay, I don't know. This is some Python library stuff. Direct show base. I have no idea what that means. Okay. Well, that's a little bit annoying. Well, we can see our buffer exists. There is data going into it, and the amount of data is, I think, congruent with the amount of voxels. Let's see. I'll make it, data is going to be floats, but they're not floats. I'll make them ints. Just apply, and then have a look. How long do we get one for? Okay, 100 and what, 27 is it? 119. Okay, so 119 with one triangle. Does that make sense? I don't think it does. Or maybe it does. 7 by 7 by 7. You know, we didn't add that check, did we? To make sure that we're not on the edge. We should do that. That check I'm talking about is in this guy's code. There's a check here to make sure that we're not on the edge, which will give us invalid data, so we should do that. Where is it? Local invocation ID. Yeah, okay. So chunk size is going to be 8, so we'll just say 8 minus 1. I know that seems silly, but I'm probably going to replace all the 8s with the chunk size variable later. Okay, we just want to return out of here and do nothing. I think that might be good. Okay, we got our frames, that's great. I should probably just capture one frame, but it's black, so I don't know if it's working. Cool, I'll get rid of this. What? Okay. Resource inspector, buffer 48 again, view contents. Alright, we just got ones again. How many ones did we get? Is it 119 again? No, it's a different amount. 102. 102. Okay. Let's think about that. So 8 by 8 by 8 is 512, divided by 8 is 128, and then minus 8 times 3 is 8 times 3 is 24. Yeah, I think that actually makes sense. You'd only have 102 groups of triangles, but they wouldn't all be one triangle, would they? They might be. Let's have a look at the data. So these are all supposed to be triangles, so I guess we'll say we can group this in. Can we say struct spec3 A, B, C? Is that gonna work? Failed to parse declaration struct data. Failed to parse declaration B. Okay, fine. Be like that. What about that? Is that going to work? Yeah, there we go. So we should have triangles here. Is that a triangle? Yes, it is, I think. What about this one? Suspiciously large numbers though, which is why I'm confused. And then these ones are all tiny. Yeah, this is not working yet. Not working yet. Okay. Well, unfortunately, I'm going to have to get going. This is the first failed stream so far, but that's okay. I will probably work on this a little bit more tomorrow night or something, but I'll be back. You know what? I'm not going to make any promises, but let's just say I should be streaming more often. So, I want to thank everyone who tuned in. I want to condemn the person who spammed something about getting more viewers in chat if I pay for them. And I wish you all the best. So, take care and goodbye. And goodbye.